Throughout the history of the world, over 5 billion different species inhabited this planet. The Earth as we know it today would not exist without the contribution of living organisms, and as such, we see life as the essential, exceptional characteristic of planet Earth. Within about 3.5 billion years, life in very simple, single-celled forms mysteriously emerged, branched into eukaryotic, bacterial and archaeal cells, and finally developed into complex species as we see them all around us today. Organisms such as those chickens, the worms they're eating, or even human beings like myself are highly organized systems that use a lot of energy in order to sustain themselves, in order to exist. Throughout evolution, we believe non-living matter transformed into living cells, which became more complex over time. But what distinguishes the living? How did this fascinating phenomena, immense concentrations of energy, emerge? Just like the smoke ascending from a cigarette, immediately dispersing in the air, energy in our universe tends to strive towards a more even distribution, equilibrium. A stable system where all acting forces are balanced or cancelled out. And as equilibrium increases, so does another essential quantity, entropy. This concept was first coined by the German physicist Rudolf Clausius in 1865, later taken up by influential minds such as Ludwig Boltzmann, and continues to be highly relevant today. In its physical application, the entropy in a closed system describes the internal energy which is unavailable to do work in the system. The second law of thermodynamics tells us that closed systems such as our universe naturally tend towards more entropy. This means that energy in ordered states always strives towards a less dense distribution, with more degrees of freedom on a microscopic level. In order to understand the properties of entropy, it is essential to note that entropy is not a qualitative but a quantitative measure, allowing us to calculate this observed disorder of a system. It is derived from the first law of thermodynamics, which states that the change in the internal energy of a closed system is equal to the amount of heat supplied to the system minus the work done by the system on its surrounding. From this starting point, through the application of several mathematical and physical laws, we arrive at Boltzmann's famous equation, where W denotes the multiplicity or probability of a system and K is the Boltzmann constant. How life, a system so far from thermodynamical equilibrium, came into existence in a universe where the entropy is ever increasing is truly a mystery. Let's have a look at how scientists try to explain the emergence of life.
One scientist had the right idea in mind and knew that for life to appear, equilibrium must be broken, an organization of matter has to be made. He put the right parts together, added a bit of lightning and...
It's alive. It's moving. It's alive. Oh, it's alive. It's alive. It's alive. It's alive.
In the 20th century, Professor Harold Urey and his student Stanley Miller were considering something very much alike, but instead of trying to recreate life from dead organic matter, they tried to create organic building blocks under Earth's presumed conditions at the dawn of life. In the atmosphere at the time there was carbon dioxide, nitrogen, hydrogen sulfide and sulfur dioxide, which created a reducing atmosphere, as we have in here. Underneath this atmosphere there was a water solvent containing ammonia, methane and a drop of hydrogen. Now we just do what Urey and Miller did in their experiment. We add this specific atmosphere to this specific solvent, and not the least bit important, we add a bit of heat. Wow, who would have thought? It looks like amino acid and sugars actually appeared in our experiment and are floating around in the liquid. But how could such a thing have happened? I wonder. The carbon dioxide in the air must have somehow reacted with the methane in the water, producing formaldehyde. At the same time, carbon dioxide and methane both reacted with the ammonia in the water to produce hydrogen cyanide. Adolf Strecker had already long before theorized how this formaldehyde, cyanide and ammonia could have produced the most basic amino acid, glycine, through his Strecker reaction. Around the same time, Alexander Buterov showed us how two formaldehyde molecules can react with one another to make ribose, life's most common sugar. Although Urey's and Miller experiment was a great success, it was considered overrated by a lot of other scientists at the time, and after Miller's death, others went through his original results and found that he had tampered with them to better match his theory. In his original results, more than 20 different amino acids occurred, more than present in today's life.
Despite all the progress and effort made towards understanding the mystery of how life could have emerged, we are still very far from having a definitive answer. Who knows, perhaps the question will be answered in our lifetime. For the time being, the gaps in our understanding are left to be filled by our imaginations.